Okay, so I got cut off on that last video, so we'll finish this one up right here and figure out how I did this one right here. Again, these ones are conjugate pairs, H2S and HS, also NH3 and NH4. Okay, so since we want an acidic buffer, we could calculate which one's going to be an acidic buffer by taking the negative log of their Kas. Or a simpler way to do it, since we just have two answers right here, we could just pick one, which one is the stronger of the two acids. Is it H2S or is it NH4? So let's take a look. And I got a million markings on all of these things here. So we're just going to clean this up a little bit. So here's H2S right here, and here's NH4. H2S is a stronger acid, and so therefore H2S is a stronger acid, so therefore it's probably going to be H2S. I'm just going to take like the negative log of this. Okay, and yeah, so this is my thing right here. Now, if you took the negative log of H2S, it's going to come out to pH 7 pretty much. But since it's diprotic, it'll actually come out to be slightly acidic. So in case you're calculating it. 4 samples of rain are collected from different geographic regions, and the pH is measured for each sample. Okay, so which of the above samples would be considered classified as acid rain? So rain is naturally acidic. Rain is typically has a pH of 6 or between 6 and 7, really. Might be even as low as 5.5-ish in some cases. And the reason why rain is naturally acidic is because of the carbon dioxide that is in rain. Carbon dioxide combines with water and makes carbonic acid, H2CO3. Now, what is acid rain? Acid rain is a specific thing where pollution is the cause of making the rain acidified. And it's mainly something like SO2, like sulfur dioxide in the air that combines with the water and makes H2SO3 or sulfurous acid. When SO2 is in the air and combines with water, the pH really, really drops down to like 4 or 3, or even possibly even lower than that. And so that is considered what acid rain is. So pH of 6, even though it's slightly acidic, is considered normal. So what is acid rain? These ones are going to be acid rain. Those are way too low. So samples 1 and 2. These are considered normal. Which of the following best describes the process of oxidation? So if you're in my class, hopefully you remember that losing electrons is oxidation. Okay. So so electrons gained, oxygen given off. No, that's definitely not right. So losing electrons is oxidation. Now, let's imagine we had something like Cr2 plus, and it turns into Cr3 plus. Okay, so in order to do this, it had to lose 1 electron, and since electrons are negative, it becomes more positive, and that's why when it goes from Cr2 plus and turns into Cr3 plus, it lost 1 electron. But here's an interesting thing. Say if I did the oxidation number of Cr2 plus, it would be plus 2. That's the oxidation number of Cr2 plus. The oxidation number of Cr3 plus is 3 plus. So what happens is when something is losing electrons, the oxidation number actually increases. So the process in which the oxidation number increases, because it's going from 2 to 3, that is oxidation, kind of. Maybe not the best definition of what oxidation is, but it's the only thing that's here that is like correct. Okay, what is the next question says, what is the oxidation number of nitrogen in mercury 2? This is important because it says that 2 under there, compound in this thing right here. Now, oxidation number is loosely tied to ion number, or the, yeah. So since it's called mercury 2, Hg is going to be considered 2 plus. Okay. Now, we have 2 nitrogens, so that's going to be like plus 2x. Okay, so we have 2 nitrogens. We have 6 hydrogens. Now, hydrogen has a value of 1, so that's going to be plus 6. Chlorine typically has a value that is negative 1, and so since we have 2 of them right here, that's minus 2. Okay, and that's going to equal 0. Okay, so I'm just going to like combine my like values. I have that plus 2 and minus 2, so I have actually 2x plus 6 equals 0 right here, and so now I have 2x equals a minus 6 from both sides, minus 6, and divide both sides by 2. I have x equals minus 3, right, like that. Okay. Which of the following combinations will react spontaneously under standard conditions? So let's just go through these things right here. Silver and bromine. Silver solid and bromine liquid. So let's go down, down, down. Okay, here we go. So here's silver. And oh, there's bromine right there. Okay. So since it's like a negative slope right here, that's actually going to be our answer right here. That'll react spontaneously. So yeah, totally this one. Just to kind of show you what wrong answers are, nickel and cobalt 2. Let's say nickel and cobalt 2. The hardest part is finding these things. Here's nickel and cobalt 2. And you probably have found it at home, and I'm struggling still. Okay, I can do it. Cobalt 2. Cobalt. There it is. Okay. So since it's going in this direction right here, this positive, like going in from this is non-spontaneous. Non-spawn. If you want to know why is this non-spawn, it's because if hypothetically this thing would react, if nickel turned into nickel 2 plus, what would happen is that nickel turning into nickel 2 plus, well, the nickel 2 plus is a stronger oxidizing agent than cobalt 2 plus. And so then it would just want to turn back into nickel solid. And if cobalt 2 plus turned into cobalt solid, well, that's cobalt solid is a stronger reducing agent than nickel solid. And so it just wants to turn back into cobalt 2 plus. So this is considered a non-spontaneous reaction. And we don't even have to do any more of them because, well, we already found our answer. But I want to show you what one of the wrong answers would look like. Okay. Number 42 here. Which of the following is correctly balanced reduction half reaction? So I was hoping that they were going to do some oxidation ones in here, but everything is gaining electrons, so we can't even eliminate anything like that. Okay. I'm just going to take I'm just looking at this thing right now, and one of the first things I'm starting to notice is the charges are all messed up. So let's take a look at this first one right here. So rather than balancing each and every single one of these things properly, just like pick one thing and see if they're balanced. Like you can pick the carbons and you're like two carbons, and two hydrogens and two hydrogens and two nitrogens and two nitrogens. Everything is looking pretty good. But look at the charges. This side right here is 2 plus, 2 positives, and this side right here is 2 negatives. Okay, that's not balanced. Okay, it has to have the same charges on both sides. This one has 6 negatives here and 6 positives on this side. That's not balanced. 3 positives, 3 negatives, so that cancels out, but we still have 1 negative. So this is 1 negative and no charge. That's not balanced. Now let's take a look at this one right here. 6 positives, 4 negatives. So that has a total charge of 2 positives. And then we have 2 positives on this side. That's the only one that balances the charges. So it's going to have to be D. Number 43, which of the following ion concentrations could be determined by a redox titration using nitric acid? Assume the use of a suitable indicator. So nitric acid, which of the following ion concentrations could be determined by a redox titration using nitric acid? And we have Br, nickel, Fe2 plus, and Mn. Okay, so nitric acid is HNO3. Okay, this is a table question. I can try to memorize these things. Br minus, Ni2 plus, Fe2 plus. Okay, and one other one that I can't remember right now. Br minus, what was the second one? Ni2 plus, Fe2 plus, Mn2 plus. Fe2 plus, Ni2 plus, Mn2 plus. I think I mixed up some of the order. Br minus, Ni2 plus, Fe2 plus, Mn2 plus. Br, Ni, Fe, Mn. Ni, Fe, Mn. Okay, I got it. Okay, I did it. So N plus nitric acid. So let's find nitric acid. That's the step number 1. Okay. There it is. Okay, so nitric acid is acid plus nitrate. That's nitric acid. Okay, so let's take a look at some of these things and see what we got here. Okay, Br minus right here. That can't be used. That's a non-spontaneous reaction. So that one kind of sucks. Let's take a look at Fe2 plus. Okay, so we said that one's wrong. There's Fe2 pluses right here. So this could be used. Fe2 plus could be used because that's spontaneous. Okay. Let's take a look at Ni2 plus. No. Here's Ni2 plus. They're both oxidizing agents. Mn2 plus. No. Also an oxidizing agent. Yeah. So that one's easy. Fe2 plus is my answer. Okay, number 44, a solution of KMnO4 is standardized using oxalic acid according to the following equation, blah, blah, blah. The titration of 0.134 grams of oxalic acid requires 24 mils of KMnO4 solution. What is the molarity of KMnO4 solution? This is just a stoichiometry question. I'm going to do stoichiometry. So I'm going to take 0.134 grams of oxalic acid, and I'm going to change it into moles. So 1 mole of oxalic acid is 2. 12 times 2 is 24. And 16 times 4 is 64. So 26 is 80, that's 90. Okay, so now I'm in moles of oxalic acid. And I don't want to be in moles of oxalic acid. I want to be in moles of KMNO4. So it is, here's my oxalic acid, which is 5. So I want out of oxalic acid. So I'm going to put oxalic acid on the bottom, H2C2O4. And I want MnO4. So it's going to be 2 MnO4. Okay, which is the same as K MnO4. It's just that the K is the spectator. In this case, we didn't bother writing it. So it'll be the exact same as KMNO4 as MnO4. Anyways, so now if I did this, grams cancels with grams, oxalic acid cancels with oxalic acid, and now I'm in moles of MnO4 or KMNO4. But I don't want moles of KMNO4. I want molarity. So I'm going to divide by my liters of KMNO4, 0.02470 liters. And that is actually going to equal 0.134 divided by 90 times 2 divided by 5 divided by 0.0247, and that equals 0.02411156. Okay, or in other words, 2.41 times 10 to the minus 2. That one. Okay. What is the cathode reaction for this cell right here? So we have inert, we got bromine right here, and we have some copper right here. So we need to go find those things on our table right there. Just going to erase this so I can see a little bit easier. So bromine and copper. Here's bromine, and I think it said copper 2. So copper 2. I just want to double check. Yeah, copper 2. Okay. So what's going to be reacting right here spontaneously for this electrochemical cells? Br2 and Cu solid. So it's going to be Br2. Br2 is going to be gaining 2 electrons and turning into 2 Br minus. Is going to be gaining 2 electrons and turning into Br minus, like that. Okay. And it says what is, and then Cu solid is going to be losing 2 electrons and turning into Cu2 plus 2 electrons. And here is my gaining electrons is reduction, is the cathode. So this is my cathode reaction. This is my anode reaction. What is the cathode reaction for this thing? We just already solved that. So that's going to be my cathode reaction right there. This one relates to this one as well. Which of the following best describes the movement of potassium ions and electrons as the cell operates? I'm just going to zoom out a tiny bit. Okay. So the electrons are going and flowing into here. This side is gaining these electrons. Okay. And so the electrons are leaving that side right there. Since the electrons are coming into the cathode side, this starts to become very, very negative. Okay. And in order to counteract that, the positive K is going to go in there. So potassium is going to move towards the cathode side. So potassium is going towards the cathode side, which is the platinum side. Okay, so it's going to be one of those two answers right there. Now, the electrons are going to move. We already wrote that out. The electrons are moving towards the cathode side as well, or the platinum. So this one right here, this one right here. So that's my answer right there. What is the standard cell voltage? So my formula for voltage is voltage equals cathode minus anode. Okay, so my voltage equals my cathode 1.09 minus 0.34. 1.09 minus 0.34. And that's going to be 0.75. Okay. If it's making electricity, if it's electrochemical, it can't be negative. Okay, that'd be an electrolytic. Okay. A student constructs 3 standard electrochemical cells, and and these are the results of everything right here. So earlier in the previous question, we said that voltage is cathode minus anode, and that's what it is. So so in this one right here, I'm going to go voltage, which is 1.18, is equal to cathode PD minus GA. Okay. And this one right here is 0.16 equals cathode CD minus GA. And this is some voltage. I'm just going to call it X, and that is going to equal PD minus CD, like that. Okay, and so now I need to find out how much electricity this one right here is going to be making. So what I can do is in this formula right here, this is the one that I really care about, and I only get this information these informations right here. And this formula right here doesn't have GA. So what I'm going to do is I'm going to rearrange the cell 1 so that it's equal to GA. Okay, so I'm going to go like 1.18 minus, I'm just rearranging it, minus PD equals negative, I'm going to keep it actually to negative GA, like that. And then for cell 2, I'm just going to rearrange the formula again. I'm going to subtract CD from both sides. So it's going to be 0.16 minus CD equals, again, minus GA. Now what I can do is I can make these two things equal to each other, okay? So if I make them equal to each other, I'm going to go 1.18 minus PD equals, since they're both equal to GA, they're both going to be equal to each other, 0.16 minus CD, like that. So now that I have kind of that, I'm going to rearrange this formula so that it's going to say whatever it is equaling to PD minus CD. Okay. So I'm just going to erase this little box I put around there. So I'm going to add PD to both sides, and then I'm going to minus 0.16 from both sides. And that's going to give me 1.18 minus 0.16. And since I'm adding PD to both sides, I'm going to go PD minus, and I'm keeping that minus CD right there, like that. Okay. And oh, look, this chunk right here looks really like this chunk right here. Okay. And so, is that the right color? So what I can change, keep going with this formula, is 1.18 minus this is 1.02 equals PD minus CD. Okay, and that's my answer. Which of the following would prevent the corrosion of an iron nail? Store in chlorine gas. Let's take a look. Okay, iron nail. So we're dealing with like pure iron nail. So not that one. Pure iron, Fe, there it is. So there's iron nail. And if we put it in chlorine gas, no, that would react really, really well together. So that would be a spontaneous reaction, and chlorine gas would take care of it. Store the nail in dry air. If there's no water to help facilitate making like ions, then this is a very, very good thing. Storing in dry air will really, really help. Store the nail in a beaker of distilled water. No, like the oxygen can dissolve in that distilled water still. And now you have distilled water, which is a really good facilitator for making iron ions and stuff like that. Store the nail wrapped in cobalt in a beaker of distilled water. Let's take a look. Where is cobalt? There it is. No, this won't work at all. Because iron is a stronger reducing agent than cobalt. So iron would be preferred to react over cobalt. If that last answer said store that iron nail in chromium, zinc, manganese, magnesium, stuff like that, that is like further, that's a better reducing agent, then yeah, that could be a potential answer. But cobalt, that's just a wrong answer. So yeah. Okay. One more question and then we're done. Electrolytic. Okay. So here's our negative thing right here. I always do this whenever I see an electrolytic cell. The electricity is going to go down here, making this electrode negative. Since this one's gaining electrons, this is the cathode right here. And that makes this the anode. Okay. Anyways, let's look at the question. Which of the following describes the anion movement and electrode masses for the above cell? Okay. So the anion movement, so the anion is the NO3. Now, since the electrons are leaving it, that means this will be positively charged. So these anions, which is a fancy way of saying negative ions, is actually going to be attracted to this one right here. So the anions are going to be attracted to the copper right here. So the anions want to move to the copper right there. Okay. Now the silver that's right here, which is Ag plus, wants to go towards the negative. The positive and the negative are attracted. And the silver will turn into silver solid. And since it's turning into silver solid, this cathode is going to increase in size. It's going to increase in size because it's going to get a thick layer of silver on the outside of it. Okay. Now, as the copper is losing electrons, copper, which is going to be losing electrons, turns into copper 2 plus. And so copper will start to come out into solution right there. And so this anode is going to decrease in mass. And so that's our answer right here. Okay. And here's our actually data booklet was put into the middle of this thing right here, and this here, and this is our first thing right here. Consider the reaction. State two different methods that would increase the rate of reaction and explain each in terms of collision theory. Okay, since we have a heterogeneous mixture of solids and gases, one thing that we can do is we can